What if everything we think we know about the universe is just the tip of the iceberg, a small, illuminated fragment in an ocean of cosmic mysteries waiting to be discovered? Picture the vastness of space not as an empty void, but as a dynamic frontier where light and shadow dance in ways that continually surprise us. For centuries, humanity has gazed up at the night sky, searching for patterns, meaning, and answers. Yet with every technological leap, every new telescope and satellite we send into the heavens, we uncover not just solutions, but deeper, more tantalizing questions. It's at this very intersection where hard data meets profound darkness that some of the most disruptive anomalies in modern astronomy emerge, challenging our assumptions and reshaping what we believe is possible. Think about it. We live in an age where we can map the echoes of the Big Bang, track the motion of galaxies millions of light years away, and even listen to the faint whispers of radio signals from across the cosmos. But for every answer these tools provide, they also reveal something unexpected, a signal that shouldn't exist, a motion that defies gravity, a structure that breaks all the rules. These aren't just small glitches in our understanding. They are full-blown cosmic puzzles that force scientists to rethink fundamental laws and principles. And what's truly captivating is that these mysteries aren't confined to academic journals or research labs. They resonate with anyone who has ever looked up at the stars and felt that stirring sense of wonder. In this video, we're setting out on a journey to explore 20 of the most compelling disruptive anomalies ever documented, phenomena that straddle the line between known science and utter mystery. From enigmatic signals that hint at intelligence beyond our world to gravitational oddities that suggest our universe is far stranger than we ever imagined, each of these discoveries offers a glimpse into the hidden workings of reality. We'll dive into the data, hear from the researchers on the front lines, and unpack why these anomalies matter not just to astronomers, but to all of us trying to make sense of our place in the cosmos. So settle in and open your mind, because by the time we're done, you may never see the night sky the same way again. Picture this. It's a warm August evening in 1977, and at Ohio State University's Big Ear radio telescope, astronomer Jerry Amon is sifting through reams of data printed on continuous green and white paper. This was a routine part of the search for extraterrestrial intelligence, or SETI, a patient listening for any whisper against the overwhelming static of the cosmos. Then his eyes land on a sequence of alphanumeric characters representing a signal so potent, so perfectly configured, that he circles it in red pen and simply writes, "Wow." Next to it, that single, spontaneous exclamation would give a name to one of the most enduring mysteries in astronomical history, a signal that to this day has never been satisfactorily explained. What made this signal so extraordinary wasn't its duration, a mere 72 seconds, but its impeccable profile. It was a strong, narrowband radio signal, meaning it was concentrated on one specific frequency, just like an artificial transmitter would be. Crucially, that frequency was 1420 MHz, which is a protected band internationally. It's a quiet channel where earthly transmissions are forbidden, making it an ideal place for anyone or anything to broadcast a clear message into the galaxy without interference. The signal also intensity, rising and then falling in a clean curve as the telescope's fixed dish observed it, perfectly matching what you would expect from a distant, point-like source passing through the field of view. It was, by every technical measure, the kind of signal the project had been built to find. In the decades since, the search for a repeat or an explanation has become something of a holy grail in astronomy. Countless follow-up observations have been aimed at that same patch of sky near the constellation Sagittarius, using far more sensitive equipment than the Big Ear telescope. Yet the silence has been absolute. Not a single whisper of a repeat signal has ever been detected. This profound lack of additional data is what fuels the mystery and pushes theorists to consider a wide spectrum of possibilities. On one end, there are natural explanations. Could it have been an unknown cometary emission, a burst of energy from a passing asteroid, perhaps an intermittent stellar phenomenon we don't yet understand? Each idea has been proposed, but each also struggles to fully account for the signal's unique and powerful characteristics. Then, of course, there is the more profound and admittedly more thrilling possibility that the WOW signal was exactly what it appeared to be, a deliberate broadcast. A cosmic hello that swept past our planet for just over a minute before vanishing back into the interstellar void. If that is the case, the implications are staggering. It would mean we are not alone, and that another intelligence, perhaps from a star system hundreds or even thousands of light years away, possesses the technology and the desire to communicate. Yet, the very brevity of the signal also presents a deeply humbling thought. It's a stark reminder of the sheer scale of the universe and the limitations of our own technology. We might have just one chance, one fleeting 72-second window, to catch a message that took millennia to arrive. It underscores that for all our advanced listening posts and data processing power, we are still essentially stargazers on a shoreline, waiting for another bottle to wash up with a message inside, never knowing if or when it might come. The true legacy of the WOW signal lies not in providing answers, but in perfectly framing the question. It sits at that perfect intersection of data and darkness, a solid, verifiable piece of information that emerged from the void, only to retreat back into it, leaving behind a trail of awe and speculation. It challenges our methods and our patience, proving that the universe is capable of delivering profound mysteries in the briefest of moments. This anomaly doesn't just make us wonder about who might be out there. It makes us reconsider our entire approach to listening, waiting, and wondering in the vast and silent cosmic ocean. But if the WOW signal leaves us wondering about what might be hiding in the silence, the next anomaly suggests that the cosmos itself might be in motion due to forces we can't even see, let alone understand. Imagine the entire universe not as a static expanse, but as a river flowing in a direction we're only beginning to perceive. This isn't a metaphor, it's a phenomenon astronomers call dark flow, and its discovery sent shockwaves through the field of cosmology. While studying the subtle motions of enormous galaxy clusters, scientists made a startling observation. These massive structures, each containing thousands of galaxies, weren't just moving apart due to the expansion of the universe as expected. They were also drifting together in a specific, coordinated direction at astonishing speeds of over 2 million miles per hour. It was as if an immense, unseen hand were gently pulling them toward a point far beyond the edge of everything we can observe. This coordinated motion presents a direct challenge to one of the most fundamental principles in cosmology, the cosmological principle. This idea states that on a large scale, the universe should be homogeneous and isotropic, meaning it looks roughly the same in every direction and no place is special. The observed dark flow blatantly contradicts this. It suggests that on the largest scales, the universe isn't uniform at all, but might be structured and influenced by something enormous lying outside our cosmic horizon. The data supporting this isn't flimsy. It comes from precise measurements of the cosmic microwave background, the afterglow of the Big Bang. By studying tiny temperature fluctuations in this ancient light, researchers can map the direction and velocity of these galaxy clusters, and the pattern is too consistent to ignore. So what could possibly be exerting such a profound gravitational pull on entire clusters of galaxies? The most mind-bending theory points to the influence of other universes. In the multiverse scenario, our universe might be just one bubble in a vast cosmic foam, and the gravitational tug from a neighboring universe, an entirely separate reality with its own physical laws, could be the source of this dark flow. Other explanations involve colossal structures made of unknown types of matter or energy that reside beyond our observable limit. Whatever the cause, dark flow forces us to confront a humbling possibility. The universe we can see with our most powerful telescopes, a sphere nearly 93 billion light-years across, might only be a small part of a far grander, interconnected reality. It's a reminder that the darkness between the stars isn't empty. It might be teeming with the gravitational echoes of realms we can never directly visit, shaping the fate of everything we can see from the shadows. Yet for all its vastness and potential, the cosmos remains eerily silent. This profound contradiction is the heart of the Fermi Paradox, named after physicist Enrico Fermi, who, during a casual conversation in 1950, posed a deceptively simple question. If intelligent life is statistically likely, where is everybody? Decades of scientific progress have only deepened the mystery. Our telescopes have confirmed thousands of exoplanets, with estimates suggesting there could be over 100 billion Earth-like worlds in our galaxy alone. We understand the chemistry of life's building blocks and have found them scattered across nebulae and icy moons. The data overwhelmingly suggests that the ingredients and conditions for life should be commonplace. And yet, when we point our most sensitive instruments at the sky, listening for a whisper of communication or scanning for signs of vast engineering, we are met with a resounding, unsettling quiet. This great silence has spawned a spectrum of theories, each attempting to explain the void. One unsettling possibility is the concept of the Great Filter, a hypothetical barrier so difficult to overcome that it prevents life from progressing to an interstellar stage. This filter could lie in our past, meaning the emergence of intelligent life itself is a near miraculous fluke. Or, more ominously, it could await us in our future, a challenge like advanced technology leading inevitably to self-destruction through war or environmental collapse. Perhaps every civilization that reaches a certain point of technological maturity inadvertently creates the tools of its own demise, a cyclical tragedy playing out on silent worlds across the galaxy. Other explanations are less grim but equally mind-bending. Maybe we are simply too early or too late to the cosmic conversation. Intelligent civilizations could have risen and fallen billions of years ago. Their signals already passed us by, or the first great empires might be yet to emerge in a universe still young. Alternatively, our methods of searching might be hopelessly primitive. An advanced civilization might not use radio waves at all, instead employing neutrino communication or technologies we cannot yet conceive. Their presence could be all around us, encoded in the fabric of spacetime or hidden in plain sight, but so far beyond our comprehension that we fail to recognize it as artificial. They might even be choosing to remain silent, observing us like a cosmic wildlife preserve, adhering to a strict principle of non-interference. The Fermi Paradox ultimately forces a humbling introspection. It suggests that the darkness between stars isn't merely an empty void. It could be a canvas reflecting our own ignorance, or a library containing truths we are not yet advanced enough to read. This anomaly challenges not just our science, but our philosophy. Are we a miraculous accident, a lonely beacon of consciousness in a sterile universe? Or are we simply the newest residents in a crowded neighborhood, too naive to hear the conversation happening just next door. The silence is not an absence of data, but a data point in itself, one that compels us to question everything we assume about life, intelligence, and our place in the cosmic story. While the Fermi Paradox leaves us pondering the profound silence of the cosmos, the universe occasionally responds not with silence, but with a sudden, deafening shout. Imagine a flash of radio energy so intense that it, for a single millisecond, outshines entire galaxies. This isn't a slow-building signal from a potential intelligence. This is a cosmic blast wave, a scream of raw power from the deepest reaches of space. These events are known as fast radio bursts, or FRB, and they represent one of the most explosive and enigmatic anomalies in modern astronomy. The story of their discovery begins not with a shouted, "Wow!" but with a patient sifting of old data. In 2007, astronomer Duncan Lorimer and his student were reviewing archival recordings from the Parkes Radio Telescope in Australia when they found a single, colossal spike of energy that had occurred years earlier. It lasted just 5 milliseconds, but in that blink of an eye, it released as much energy as the Sun does in over 80 years. For a long time, it was considered a curious one-off, perhaps a local glitch. But then another was found, and another. Today, sophisticated observatories like CHIME in Canada are detecting them regularly, cataloging hundreds of these events, and each one is a monumental puzzle. They arrive from all directions in the sky, originating billions of light-years away, far beyond our own Milky Way. What makes FRBs so fascinating to scientists is their dual nature. Some are lone wolves, tremendous bursts that detonate once and are never heard from again. Others are repeaters, firing off multiple signals from the same location, but on a schedule that seems utterly random and unpredictable. This distinction is crucial because it strongly suggests there are at least two different types of astrophysical engines capable of producing these incredible blasts. The repeating FRBs have allowed astronomers to finally pinpoint their home galaxies, confirming they originate in distant, often unremarkable galaxies, which rules out them being signals from an advanced civilization. Their power is simply too immense to be artificial. So what natural phenomenon could possibly be this violent and this brief? The current best guesses involve some of the most extreme objects in the universe. One leading candidate is a highly magnetized neutron star known as a magnetar. These city-sized corpses of dead stars possess magnetic fields so powerful they could strip the information from a credit card from halfway across the moon. A starquake on the surface of a magnetar, a sudden snapping of its crust under immense strain, could theoretically unleash a fire hose of radio waves shooting out into space. Another compelling theory involves a special kind of binary system, perhaps a neutron star and a black hole in a close, violent dance. As they spiral inward toward a catastrophic collision, their immense gravitational and magnetic fields could interact to create a final, brilliant flash before the darkness of a merger. Yet for every theory that fits one observation, another FRB seems to break the mold. Their sheer power and the vast distances they travel force us to confront the limits of our current physics. They are like cosmic lightning, incredibly bright, Chinese letter LY brief, and born from processes we are still struggling to fully comprehend. Each detection is a gift of pure data, a tiny, bright flicker that illuminates the darkness for a fraction of a second, giving us a glimpse into the most energetic and chaotic corners of the universe. And just as quickly as they appear, they vanish, leaving behind only the echo of their mystery and the thrilling certainty that the cosmos is far more dynamic and explosive than we ever imagined. While we search the skies for fleeting signals and ponder the silence, our own galaxy is caught in a relentless cosmic current, pulled by a hidden force of unimaginable scale. This isn't a gentle nudge, it's a gravitational towline that has our entire Milky Way, along with our local group of galaxies and thousands of others, moving at over 1 million miles per hour toward a specific point in the constellation Centaurus. Astronomers call this mysterious focal point the Great Attractor, and its very existence is a humbling lesson in how much of the universe remains hidden in plain sight, shrouded by the very stuff that makes up our cosmic neighborhood. The central challenge in unraveling this mystery is a region astronomers poetically call the zone of avoidance. This isn't some mystical barrier, it's a simple yet profound observational blind spot. It refers to the plane of our own Milky Way galaxy, which from our vantage point on Earth appears as that beautiful, dense band of stars arching across the night sky. But within that luminous river of light lies a problem: immense clouds of interstellar gas and dust that blot out the visible light from anything behind them. It's like trying to see a distant mountain range through a thick, perpetual fog. For centuries, this zone effectively cut our map of the universe in half, hiding whatever lay directly behind the core of our own galaxy. And as fate would have it, the Great Attractor lies almost perfectly positioned within this zone, its secrets veiled by the crowded heart of the Milky Way. We wouldn't even know this colossal something was there if not for its relentless gravitational pull. You can't see it, but you can most certainly measure its effects. By meticulously tracking the motion of galaxies around us, scientists could map the flow, the coherent river of galaxies all drifting in the same direction. The data pointed irrevocably to a single, massive source of gravity. The initial calculations were staggering, suggesting an immense concentration of mass, perhaps equivalent to tens of thousands of Milky Ways, all clustered together in a region of space that, from our viewpoint, was seemingly empty. This was the paradox. The motion of the galaxies was clear, irrefutable data, but the source of that motion was pure darkness. To pierce that veil, astronomers had to turn to eyes that see more than just visible light. Infrared and radio telescopes became the keys to unlocking this secret. Unlike visible light, infrared radiation and radio waves can pass through much of the obscuring dust, allowing us to map the structures hidden behind the Milky Way's bright disk. What these instruments revealed was not a single monolithic object, but something perhaps even more fascinating: an immense confluence of matter. The Great Attractor appears to be the gravitational heart of the Laniakea supercluster, a vast cosmic web of over 100,000 galaxies, including our own. Our Milky Way is merely a suburb on the outskirts of this megalopolis, and we are flowing toward its downtown core. At the center of Laniakea lies a massive cluster of galaxies known as the Norma Cluster, which acts as a central anchor point. But even this enormous gathering of visible galaxies doesn't fully account for the immense gravitational pull we feel. This is where the mystery deepens into the realm of the truly unseen. A significant portion of the attractor's power likely comes from dark matter, the invisible, mysterious substance that makes up the majority of the universe's mass, weaving its gravitational web throughout the supercluster. The Great Attractor, therefore, is likely not one single thing, but a complex combination of both the visible mass of the Norma cluster and a tremendously dense knot of this invisible dark matter, all working together to guide the motion of galaxies across an immense volume of space. This anomaly serves as a powerful reminder that the universe's greatest secrets aren't always in the far distant early cosmos. Sometimes they are hiding right next door, masked by our own limited perspective. It embodies the very essence of exploration at the intersection of data and darkness. We had the data of our motion long before we had any idea what was causing it. It took technological ingenuity and a willingness to look at the cosmos in a different light to begin mapping the contours of this hidden giant. The Great Attractor is a testament to the fact that for all our knowledge, we are still charting the geography of our own cosmic backyard, and the map is far from complete. It's a permanent invitation to keep looking, to keep developing new ways to see, because the darkness itself might be hiding the most important structures shaping our journey through the universe. Just when we thought we had a handle on the strange objects within our own solar system, the universe decided to send us a visitor from the great beyond. In October 2017, the Pan-STARRS telescope in Hawaii spotted a faint point of light moving at breathtaking speed. Its trajectory was immediately and profoundly different from anything else we'd ever seen. It wasn't orbiting the sun, it was cutting straight through our solar system on a hyperbolic path, meaning it was not from here. This was the first confirmed interstellar object ever detected, and it was given the name Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. The initial data was puzzling enough. Its brightness varied dramatically by a factor of 10 as it tumbled through space. This extreme variation suggested a truly bizarre shape, an object that was highly elongated, perhaps 10 times longer than it was wide, like a cosmic cigar or a pancake tumbling end over end. This was already unusual, as most natural objects, like asteroids or comets, are more lumpy and rounded. But the real shock came when astronomers meticulously tracked its path against the backdrop of stars. As Oumuamua slingshotted around the sun and began its journey back out into interstellar space, it wasn't following a perfect gravitational curve. It was accelerating ever so slightly in a way that gravity alone could not explain. This is known as non-gravitational acceleration, and while it's common in comets, the explanation for it was completely absent in this case. When a comet approaches the sun, its icy surface heats up, releasing jets of gas and dust, a process called outgassing. This acts like a natural thruster, giving the comet a tiny push that alters its trajectory. The telltale sign of this activity is a visible coma, the fuzzy envelope of gas and dust, and often a tail. Every telescope pointed at Oumuamua searched desperately for this haze, for any sign of outgassing. They found nothing. The object remained stellar, a pinpoint of light with no surrounding cloud. It was accelerating like a comet, but it looked utterly unlike any comet we'd ever seen. This was the core of the anomaly, an effect without a visible cause. The lack of a clear, natural explanation is what opened the door to a spectrum of theories, from the conventional to the extraordinary. Some scientists proposed that perhaps Oumuamua was made of very unusual ices, like solid hydrogen or nitrogen. As these ices were warmed by the sun, they would sublimate directly from a solid to a gas, potentially providing the thrust without creating the dusty coma we associate with water-ice comets. Others suggested it could be a sort of cosmic dust bunny, a fragile, porous aggregate of material that was so lightweight that the gentle pressure of sunlight itself, over its large surface area, could have provided the minuscule push needed for the observed acceleration. But the most captivating and controversial hypothesis came from Harvard astronomer Avi Loeb. He and a colleague performed calculations suggesting that the acceleration could be perfectly explained if Oumuamua were an extremely thin, lightweight object, a solar sail. In human technology, solar sails are theoretical propulsion devices that use the faint pressure of photons from a star to push a giant, ultra-thin reflective sheet through space. Loeb proposed that Oumuamua's strange acceleration and unusual shape were consistent with it being a discarded piece of advanced extraterrestrial technology, a defunct light sail drifting through the galaxy. This idea, while a thrilling thought experiment, was met with significant skepticism from the broader scientific community. who argued it was an extraordinary claim based on very limited data. The true legacy of Oumuamua is not that it was likely an alien spacecraft, but that it was a perfect lesson in scientific humility. It was a cosmic postcard that arrived and departed before we had a chance to properly read it. Our best telescopes could only gather a few weeks of faint, blurry data before it vanished back into the interstellar darkness, too distant and too dim to ever study again. This fleeting encounter underscores a critical weakness in our exploration of the cosmos. We are largely passive observers. We watch and wait for objects to come to us, and when they do, we often have only a brief window to understand them. This anomaly was a direct catalyst for change. It spurred astronomers to design future missions like the European Comet Interceptor that could be prepped and launched on short notice to rendezvous with the next interstellar visitor. It highlighted the urgent need for more powerful survey telescopes like the upcoming Vera C. Rubin Observatory, which will scan the entire sky every few nights and will undoubtedly find many more of these mysterious travelers. Oumuamua was a wake-up call from the void, a tantalizing hint that the darkness between stars is not empty, but likely filled with countless strange and wonderful objects we are only beginning to imagine. It reminds us that the next time a messenger from afar arrives, we need to be ready to meet it. Yet for all the grandeur of interstellar visitors and the pull of hidden attractors, perhaps the most profound disruption to our cosmic understanding isn't a distant object, but a fundamental disagreement about the very fabric of spacetime itself. Imagine meticulously measuring a room with two different, highly precise rulers, only to find they give you two irreconcilable answers for its length. This is the essence of the Hubble Tension, a growing crisis in cosmology that strikes at the very heart of our understanding of the universe's expansion and ultimate fate. The story begins with Edwin Hubble's groundbreaking discovery in the 1920s that the universe is not static, but is continually growing, with galaxies rushing away from each other. The rate of this expansion is known as the Hubble constant, a single number that represents how fast the cosmos is stretching at the current time. For decades, astronomers have worked to pin down this number with ever-increasing precision. The problem is, we now have two supremely confident but completely contradictory ways of measuring it, and they stubbornly refuse to agree. One method involves looking at the nearby modern universe. Astronomers use brilliant, predictable stellar explosions called Type 1a supernova as standard candles. Because we know their intrinsic brightness, we can measure how far away they are and how much the light from their explosion has been stretched by the expansion of the universe. This local measurement is like using a tape measure on the room itself, and it gives us a very specific, consistent value for the expansion rate. The other method uses the oldest light we can see, the cosmic microwave background, a faint afterglow from when the universe was just 380,000 years old. This fossilized light was mapped in exquisite detail by the Planck satellite. By studying the subtle patterns and ripples in this ancient radiation, cosmologists can work backwards using our well-tested model of the universe's evolution, a recipe that includes dark matter, dark energy, and the laws of physics to predict what the expansion rate should be today. This is like using the blueprints from the room's construction to calculate its current dimensions. The shocking result is that the number predicted from the early universe blueprint and the number measured directly in the modern room disagree by a small but significant amount, roughly 10%. In the world of precision cosmology, where measurements are often accurate to within 1%, this discrepancy is a massive, glaring red flag. This tension is far more than a simple statistical fluke or a minor calibration error. It has persisted and even grown stronger as our instruments have become more advanced and our datasets larger. This stubborn disagreement suggests one of two deeply unsettling possibilities. The first is that there is some kind of systematic error, a hidden mistake or bias, in one or both of our measurement techniques that we have not yet been clever enough to uncover. Given the caliber of the scientists and the rigor of the methods involved, many find this increasingly difficult to believe. The second, and far more exciting possibility, is that our standard model of cosmology, the very blueprint we've used for decades, is incomplete. There might be something missing from our recipe of the universe. Perhaps dark energy, the mysterious force accelerating the expansion, is not constant as we've assumed, but has evolved over time, becoming stronger or weaker in ways we never anticipated. Maybe dark matter has properties we haven't yet discovered, allowing it to interact with itself or with light in subtle new ways that alter the expansion history. Or, most revolutionary of all, our understanding of gravity itself, based on Einstein's theory of general relativity, might need to be tweaked on the largest cosmic scales. The Hubble tension is a powerful reminder that data, in its purest form, is the ultimate arbiter of truth. It doesn't matter how elegant or well-established our theories are. If the observations contradict them, we must listen. This anomaly is the universe itself holding up a sign, pointing to a gap in our knowledge and inviting a new generation of thinkers to fill it, potentially leading to a revolution in physics as profound as the ones that gave us relativity and quantum mechanics. While the Hubble tension reveals a crack in our understanding of the universe's fundamental laws, another anomaly captures the public's imagination by suggesting we might not be alone in shaping the cosmos. Far from the abstract calculations of cosmology, this mystery revolves around a single, unassuming star located about 1,400 light-years away in the constellation Cygnus. Known officially as KBC 8462852, it's far more famous by its popular name, Tabby Star, nicknamed after the astronomer Tabby Baryon, who led the team that first brought its bizarre behavior to the world's attention. What makes this star so captivating isn't its size or age, but its baffling, unpredictable flickering, a pattern of dimming so extreme and irregular that it defies all conventional explanation and has spawned some of the most creative scientific hypotheses in recent memory. The story of its discovery is a testament to the new era of big data in astronomy. The star was first flagged by volunteers of the Planet Hunters Project, a citizen science initiative that invited the public to sift through the immense trove of data collected by NASA's Kepler Space Telescope. Kepler's primary mission was to find exoplanets by watching for the telltale, periodic dimming of a star that occurs when a planet passes in front of it. These dips are usually tiny, predictable, and rhythmic, like a perfectly timed heartbeat. But the volunteers tagging this star's light curve kept noting something was terribly wrong. Instead of small, regular dips, they saw monstrous, chaotic plunges in brightness. The most dramatic event saw the star's light drop by a staggering 22%. To put that in perspective, even a Jupiter-sized planet transiting a Sun-like star would cause a dimming of only about 1%. Whatever was blocking the light of Tabby Star was not a planet. It was something colossal, something covering an enormous portion of the star's surface, and something that moved in a pattern that seemed to have no rhyme or reason. The initial scientific reaction was to search for natural, albeit rare, astrophysical causes. The first and most persistent theory involved a massive, fragmented swarm of comets. The idea was that a family of exocomets, perhaps disturbed by a passing star, could have been pulled into extremely elliptical orbits around Tabby Star. As they approached the star, their icy surfaces would vaporize, creating enormous clouds of gas and dust that could block starlight in an irregular, aperiodic way. While this could explain the randomness, many astronomers found the scale required to be nearly unbelievable. To create a 22% dip, you would need a truly immense number of comets, all crumbling and venting gas at the same time, a scenario that pushes the limits of probability. Other natural explanations included a recent planetary collision that left a vast cloud of debris spiraling around the star, or intrinsic variability within the star itself, perhaps a kind of star spot activity on a scale never before witnessed. Yet each of these natural models struggled to explain the full breadth of the data, particularly the long-term dimming trend that some analyses suggested was also occurring over decades. It was this failure of conventional models that opened the door to a far more speculative, yet utterly fascinating idea, the megastructure hypothesis. In the 1960s, physicist Freeman Dyson theorized that a sufficiently advanced civilization would eventually harness the entire energy output of its home star. They might construct a vast swarm of energy-collecting satellites or platforms, now known as a Dyson sphere or Dyson swarm, encircling the star. From our distant vantage point, such a massive, incomplete construction project would appear as an irregular, non-spherical object that periodically blocks starlight in huge, chaotic chunks. The bizarre light curve of Tabby Star matched this description eerily well. The notion that we might be witnessing the signature of a Type II civilization on Kardashev scale, building its greatest achievement, instantly captured the global imagination, transforming an obscure star catalog number into a media sensation and a symbol of humanity's deepest question. The true scientific value of Tabby Star, however, lies not in proving aliens exist, but in demonstrating how science grapples with profound anomaly. It became a case study in modern investigation. When the natural explanations fell short, astronomers did not simply throw up their hands, they mobilized. They secured time on some of the world's most powerful telescopes, from the Keck Observatory in Hawaii to the Green Bank Telescope in West Virginia, training every available instrument on this one point of light. They scrutinized it across the entire electromagnetic spectrum, searching for any clue, heat signatures from dust, radio transmissions from intelligence, anything that could break the deadlock. What they found was both clarifying and disappointing for those hoping for aliens. A distinct infrared signature, dust when warmed by starlight, glows in infrared light. The observations showed that the material blocking the light was indeed dusty, not solid and opaque like a giant alien solar panel. This strongly favored the natural cometary swarm hypothesis. Yet, even with this evidence, the case is not entirely closed. The exact nature of that dust and the mechanism that creates such incredible, asymmetric clouds remains an active area of research. Tabby Star endures as a powerful icon at the intersection of data and darkness because it perfectly encapsulates the scientific process in the face of the unknown. It shows how a single, strange data point can ignite a firestorm of public curiosity and rigorous professional scrutiny. It forced astronomers to refine their models of stellar environments and consider processes they might never have imagined. And while the answer is likely a spectacularly rare natural phenomenon, the star's legacy is the reminder that we must, as a species, be prepared to ask the big questions. It challenges us to consider that the darkness around other stars might not just hold unknown physics, but perhaps one day evidence that we are not the only builders in the cosmos. But just as we grapple with the vast structural mysteries of the cosmos, our most fundamental map of reality itself presents an anomaly that strikes at a core principle of modern cosmology. This map is the cosmic microwave background, the faint afterglow of the Big Bang, and it is the single most important snapshot we have of the infant universe. For decades, it has been the bedrock of our cosmological models, its tiny fluctuations in temperature confirming our theories about the universe's composition and expansion. Yet, buried within this incredibly precise data is a strange and unsettling pattern that cosmologists have half-jokingly, half-uneasily nicknamed the axis of evil. The evil in this case isn't some malevolent force, but rather a statistical nightmare that challenges one of our most cherished assumptions, the cosmological principle. This principle states that the universe on a large scale is isotropic and homogeneous. It should look the same in every direction and have no special place or preferred axis. There should be no center to the universe and no edge. The cosmic microwave background data, for the most part, beautifully confirms this. The temperature variations are random and evenly distributed except for a few peculiar, large-scale alignments that simply shouldn't be there. These aren't just random statistical flukes, they are correlations in the data that seem to align eerily with the plane of our own solar system and the direction of the sun's motion through space. It's as if the universe's oldest fingerprint has a smudge that lines up perfectly with our own local neighborhood, suggesting a contamination or a bias we never anticipated. Scientists have proposed two broad categories of explanations, and both are deeply humbling. The first and more conservative explanation is that this is a form of contamination. Perhaps our measurements are being subtly influenced by something within our own cosmic backyard. Dust within our solar system, the magnetic field of our own galaxy, or even an unknown effect from the instruments themselves could be imprinting this strange pattern onto the pristine data from the early universe. If this is the case, the axis of evil is a monumental lesson in observational astronomy, reminding us that to see the most distant truths, we must first perfectly understand and subtract the influence of our own immediate environment. The second and far more radical possibility is that the anomaly is real. This would mean that the universe is not perfectly isotropic on the largest scales. It might have a preferred direction or a fundamental asymmetry woven into its very fabric from the moment of birth. This would force a profound rewrite of our standard model of cosmology and could point toward new, exotic physics operating in the instant after the Big Bang. The name axis of evil captures the scientific discomfort perfectly. It's a pattern that is so inconvenient, so challenging to our foundational beliefs, that it feels almost personally antagonistic to our desire for a simple, elegant, and fair cosmos. This anomaly is a powerful testament to the fact that in science, the most disruptive discoveries are often not the loud, obvious signals, but the quiet, persistent whispers in the data that refuse to go away, forcing us to question whether the darkness we are looking into is also, in some small way, looking back at us. While we search the skies for answers to grand structural mysteries like the Great Attractor or the axis of evil, some of the most compelling clues about the universe's hidden workings are emerging from the very heart of our own galactic home. Imagine the center of the Milky Way, a bustling and chaotic region dominated by a supermassive black hole, surrounded by dense clusters of stars, pulsars, and vast clouds of gas and dust. It's a place of immense energy and violent processes, and for over a decade, it has been sending us a persistent, enigmatic signal that we are only just beginning to decode. This signal doesn't come in the form of radio waves or visible light, but as a torrent of high-energy gamma-ray photons, and its origin presents one of the most tantalizing modern astronomical puzzles. This mystery began to unfold with data from the Fermi Gamma-Ray Space Telescope, an orbiting observatory designed to scan the entire sky for these highly energetic particles of light. When scientists meticulously mapped the gamma-ray emissions coming from the galactic center, they discovered something peculiar. There was a significant and unmistakable excess of gamma rays, a diffuse glow of high-energy light that couldn't be fully accounted for by any of the known celestial factories that normally produce such radiation. We know of many sources that create gamma rays in that region, spinning neutron stars called pulsars, the remnants of ancient supernova explosions, and even the intense environment around the central black hole itself. Yet when all these known contributors were added up and subtracted from the total signal, a substantial and puzzling surplus remained. It was as if an invisible, city-wide power grid was operating in the darkness, and the gamma rays were the telltale glow leaking from its hidden generators. The most thrilling hypothesis to explain this excess points directly to the most elusive substance in the cosmos, dark matter. The leading theoretical candidate for dark matter is a class of particles known as weakly interacting massive particles, or WIMP. According to the theory, these particles are their own antimatter counterparts. This means that when two WIMP collide, they would annihilate each other in a spectacular burst of pure energy, converting their mass into a shower of other particles, including gamma rays. The center of our galaxy is theorized to be the most dense region of dark matter in the entire Milky Way, a vast, invisible halo whose gravitational pull dictates the very rotation of the galaxy. If WIMP are real, this is precisely where you would expect to see the highest rate of these annihilations, creating exactly the kind of diffuse, excess gamma-ray glow that the Fermi telescope detected. For many physicists, this galactic center excess isn't just an anomaly. It's a potential smoking gun, the first indirect evidence for the existence of dark matter particles after decades of fruitless searches in underground laboratories. However, science thrives on skepticism and alternative explanations, and this case is no different. A compelling counter-argument suggests that the excess might not be from dark matter at all, but from a previously unrecognized population of extremely faint, fast-spinning pulsars. These ultra-dense stellar corpses are nature's ultimate powerhouses, capable of generating tremendous beams of radiation, including gamma rays. If thousands of these dim, ancient pulsars were clustered in the galactic center, too faint for us to resolve individually with our current telescopes, their combined emission could perfectly mimic the smooth, diffuse glow we attribute to dark matter annihilation. This debate between the particle physics explanation and the astrophysical one is a beautiful example of how modern science operates at the edge of discovery. It forces different groups of experts, theoretical physicists and observational astronomers to refine their models, challenge each other's assumptions, and push for more conclusive data. This is the essence of the anomaly, a signal emerging from the darkest, most crowded part of our galaxy that could be the key to unlocking the universe's deepest secret, or it could simply be a population of fascinating stellar objects we haven't yet learned to see. It embodies the very intersection of data and darkness in a profoundly literal sense. We are using the most energetic light we can detect to try and illuminate the nature of something that is completely invisible, something that makes up 85% of the matter in the universe, yet has eluded every direct attempt to capture it. The galactic center gamma ray excess is a cosmic treasure map where X marks a spot we cannot see, hinting that the greatest discoveries are not always made by looking at the light, but by carefully studying the mysterious glow that emerges from the shadows. While we often look to the edges of the observable universe or the hearts of distant galaxies for cosmic mysteries, sometimes the most perplexing anomalies are found much closer to home, unfolding silently on humanity's own robotic ambassadors as they journey into the void. Consider the twin pioneers of deep space exploration, the Pioneer 10 and Pioneer 11 spacecraft. Launched in the early 1970s, these rugged explorers were triumphs of engineering, tasked with the first ever flybys of Jupiter and Saturn before embarking on an endless trajectory out of our solar system. For decades, scientists on Earth diligently tracked their positions with exquisite precision, using their faint radio signals to map their paths against the background of distant stars. It was in this meticulous tracking data that engineers noticed something was amiss. Both spacecraft, now billions of miles from home, were experiencing a tiny, unexplained, and persistent acceleration back toward the Sun. It was an anomaly so small it measured only about 10 billion times weaker than the gravity we feel on Earth's surface, but it was consistent, unignorable, and defied all predictions based on Newton's and Einstein's laws of motion. This minuscule drift, which became known as the Pioneer Anomaly, represented a classic confrontation between data and theory. The numbers were clear and repeatable. The spacecraft were not quite where our best models said they should be. For years, this tiny discrepancy fueled intense speculation and excitement within the physics community. Could this be the first hint of a flaw in our understanding of gravity itself? Some theorists proposed that the anomaly might be evidence for modified Newtonian dynamics, or MUND, an alternative to dark matter that suggests gravity behaves differently at extremely low accelerations. Others wondered if it pointed to something even more profound, like the influence of unseen higher dimensions or other exotic new physics that would only manifest in the deep, quiet darkness of interplanetary space. The Pioneer Anomaly became a tantalizing beacon, suggesting that the answers to the universe's biggest questions might be hidden in the slightest of measurement errors. Yet, the most compelling chapter in this story is not about the discovery of new physics, but a masterclass in scientific detective work and intellectual humility. A dedicated team of researchers embarked on a monumental effort to solve the mystery, a quest that involved recovering decades-old engineering documents, tracking down original design schematics, and even locating vintage magnetic tape drives to read old data files. They painstakingly built an incredibly detailed computer model of the Pioneer spacecraft, accounting for every possible known force that could act upon them. The leading hypothesis focused on heat. The spacecraft were powered by radioactive plutonium, and the decay of this material generated heat that was radiated away from the spacecraft in infrared photons. The team calculated that if this heat were radiated unevenly, if, for instance, more heat were emitted from the back of the spacecraft's dish antenna than from the front, it could act like a tiny, gentle photon thruster, pushing the craft backward ever so slightly. After years of analysis, the team concluded that this anisotropic thermal radiation was in fact the most likely culprit. The data, it seemed, could be explained by the spacecraft's own design. But here is where the anomaly truly earns its place on this list. Even after this Herculean effort, a tiny sliver of the mystery remained. The thermal model explained the vast majority of the anomalous acceleration, but not quite all of it. A minuscule residual effect, a whisper of a signal, persisted in the data. This lingering uncertainty is the real lesson of the Pioneer Anomaly. It showcases that the darkness we grapple with isn't always the vast, empty blackness between stars. Sometimes it is the more intimate darkness of our own incomplete knowledge. It can be the subtle, unforeseen consequences of our own technology, a valve left slightly open, a paint chip with different thermal properties, a wire that reroutes a current in an unexpected way. These spacecraft were human-built objects, and their every bolt and circuit was known to us, and yet they still managed to produce a signal that confounded us for a generation. The Pioneer Anomaly is a humbling reminder that before we can confidently search for new laws of physics in the grand cosmos, we must first become absolute masters of the engineering and the data right here at home, because sometimes the universe's greatest secrets are hidden in the smallest, most overlooked details. Just when we think we have a handle on the grand architecture of the cosmos, the universe reveals a class of objects so faint, so ethereal, they force us to question the very definition of a galaxy. Picture a structure the size of our own Milky Way, with its majestic spiral arms spanning 100,000 light-years. Now, imagine that this vast island of stars contains only 1% of the Milky Way's stellar population. This isn't a thought experiment. This is the reality of ultra-diffuse galaxies, or UDG ghostly giants that drift through the darkness, challenging our most fundamental ideas about how galaxies are built and why they look the way they do. For decades, these cosmic phantoms remained almost entirely hidden, not because they were rare, but because they were practically invisible. Their starlight is so sparse, so spread out across their enormous volumes, that they blur into the background glow of the night sky. It took a perfect storm of technology and circumstance to finally bring them into focus. The breakthrough came with deep sky surveys and the unparalleled light-gathering power of telescopes like Hubble. By staring at the same patch of sky for extraordinarily long exposures, these instruments could accumulate enough photons to tease out the faintest of signals, revealing a population of these enormous, yet incredibly faint, galaxies that had been lurking undetected in plain sight all along. One of the most famous examples is Dragonfly 44, a UDG in the Coma cluster. From a distance, it looks like little more than a faint, fuzzy smudge. But the data revealed a shocking truth. This ghost is a colossus as wide as the Milky Way, yet so transparent you could practically see right through it. The existence of such objects creates an immediate and profound puzzle for astrophysicists. Our standard model of galaxy formation is a story dominated by gravity and dark matter. The theory goes that a massive halo of this invisible substance forms first, and its immense gravitational pull then draws in ordinary gas and dust, which eventually cools and condenses to form stars. The more massive the dark matter halo, the more stars it can gather and create, leading to a bright, dense galaxy. Ultra-diffuse galaxies turn this story on its head. How can a galaxy have the size and, presumably, the massive dark matter halo of a giant, but the stellar content of a dwarf? It's like finding the skeleton of a titan that somehow only ever grew the muscles of a child. Did these galaxies form within unusually massive dark matter halos that, for some reason, were incredibly inefficient at forming stars? Or did they originate as normal galaxies that had their gas, the raw fuel for star formation, violently stripped away? The environment seems to play a crucial role, yet the plot is thick with twists. Many UDGs are found in the crowded, violent environments of galaxy clusters, where they are battered by the gravitational tides of larger neighbors and ram pressure stripped as they plunge through the hot intracluster gas. This could certainly explain why they are so barren, as these processes can rip away their star-forming material and puff them up into their diffuse state. But then, astronomers began to find ultra-diffuse galaxies living in quiet, isolated emptiness, far from any disruptive crowds. This discovery was perhaps even more baffling. If they weren't shaped by a violent environment, what prevented them from forming stars in the first place? Their mere existence in the cosmic boondoggles suggests that the recipe for galaxy formation has a far wider range of outcomes than we ever dreamed, involving factors we are only beginning to understand, like the specific spin of a dark matter halo or the timing of early star formation that heated up gas and prevented it from collapsing. The true revolution sparked by these ghostly galaxies is how they are reshaping the hunt for dark matter. Because they contain so few stars, UDGs are considered ideal natural laboratories for studying dark matter in an almost pure form. Their mass, measured by the motion of their few stars or associated globular clusters, is overwhelmingly dominated by this invisible substance. Studying them allows astronomers to test theories of how dark matter behaves under extreme conditions. For instance, some models predict that dark matter particles can interact with each other, not just through gravity, but through other forces. The incredibly diffuse nature of these galaxies, with their matter spread so thinly, provides a unique environment to look for evidence of these interactions, which would be much harder to spot in a dense, bright galaxy like our own. Ultra-diffuse galaxies are a powerful testament to the limits of our perception. They represent an entire population of the universe that was hiding in the darkness, not because it was small or distant, but because it was built from a whisper of light stretched across a vast canvas. Their discovery is a direct result of our relentless push to collect more and better data, to look longer and deeper, and to question what we think we know. They are a humbling reminder that the cosmos is filled with subtlety and nuance, that for every brilliant spiral or blazing elliptical galaxy, there may be a silent, spectral giant drifting unseen, holding secrets about the invisible forces that truly sculpt the universe. They prove that sometimes the most significant discoveries aren't the brightest objects in the sky, but the faintest whispers that challenge us to redefine what we thought was possible. But just as we map the grand structures like superclusters and the ghostly forms of ultra-diffuse galaxies, a startling realization emerges about our own cosmic address. We have long prided ourselves on understanding that Earth holds no special place in the universe, a principle extending to our galaxy as well. The cosmological principle, a cornerstone of modern astronomy, assures us that on the largest scales, the universe is homogeneous and isotropic. It should look roughly the same in every direction, with matter distributed fairly evenly. There should be no center and no edge, no privileged vantage point. This belief in cosmic mediocrity is what allows us to extrapolate from what we see locally to the universe as a whole. Yet, a growing body of data is now suggesting that we might, in fact, be living in a very special and unusually empty neighborhood, a discovery that makes many cosmologists profoundly uneasy. This anomaly is known as the KBC Void, named for the scientists Keenan, Barger, and Cowie who compiled the evidence. Through painstaking galaxy surveys that map the three-dimensional distribution of matter around us, they and other teams have revealed a startling truth. Our Milky Way galaxy, along with our local group, resides in the center of an immense cosmic underdensity. This isn't a small pocket of emptiness. It's a gargantuan spherical void stretching over 2 billion light-years across. To put that almost incomprehensible scale into perspective, the observable universe itself is only about 93 billion light-years wide. This means we are sitting inside a bubble of relative nothingness that occupies a significant fraction of everything we can see. Within this void, the density of galaxies, clusters, and all forms of matter is about half what we would expect based on the standard model of the universe. The implications of this are deeply disruptive. If the cosmological principle holds true, such a vast void should be exceedingly rare, almost to the point of impossibility. Finding ourselves right at the center of it feels astronomically improbable, reviving the antiquated and uncomfortable idea that we occupy a special place in the cosmos. It's a modern echo of the pre-Copernican belief that the Earth was the center of the universe, but on a far grander and more startling scale. Scientists have a strong aversion to such specialness, not out of humility, but because it complicates our models. If our local patch is not representative of the whole, then our measurements of fundamental constants, like the Hubble constant, which describes the universe's expansion rate, could be skewed by this local emptiness. We might be trying to understand the entire ocean by only studying a unique and unrepresentative pond. Naturally, the response from the scientific community has been to rigorously test this finding and propose alternative explanations. Some researchers suggest that the apparent void could be a result of observational biases. Perhaps intergalactic dust within our own galaxy is obscuring our view, making distant regions seem emptier than they truly are. Others have proposed that our methods for estimating galactic distances and masses might be systematically flawed in a way that creates the illusion of a void. However, as more sophisticated surveys cross-check these results using different techniques and wavelengths of light, the evidence for the KBC void has only grown stronger. It appears to be a real feature of our cosmic environment. This forces us to confront a fascinating possibility that the universe might be structured like Swiss cheese, with vast, bubble-like voids separated by dense walls and filaments of galaxies known as the cosmic web. In this model, our existence inside one of these bubbles isn't a violation of the cosmological principle if the principle only applies on the very largest scales, beyond the size of the biggest voids. The universe could be homogeneous when you zoom all the way out, but lumpy and frothy when you look at the details. The KBC void then becomes less of an anomaly and more of a data point, urging us to refine what we mean by large scales. It challenges us to understand the hierarchy of cosmic structures and where the transition to true smoothness actually occurs. Ultimately, the KBC void is a profound lesson in cosmic perspective. It reveals that darkness isn't just the empty space between stars and galaxies. It can also be a vast, structured absence on a scale we are only beginning to comprehend. This local emptiness doesn't just hide light. It potentially distorts our entire view of the cosmos, reminding us that to truly understand the universe, we must first account for the unique properties of our own backyard. It humbles us by suggesting that even our most cherished principles might need revision based on the data we gather from our particular, and perhaps special, place in the dark. For all our grand theories about dark matter and cosmic expansion, one of the most humbling realizations in modern astronomy is that we can't even account for all the normal stuff. We're not talking about some exotic, unknown substance here. We're talking about baryonic matter, the protons, neutrons, and electrons that make up everything we can see and touch, from stars and planets to our own bodies. According to our incredibly successful model of Big Bang nucleosynthesis, which accurately predicts the abundances of light elements like hydrogen and helium, we know precisely how much of this ordinary matter should have been created in the universe's first few minutes. The problem is when astronomers add up all the ordinary matter they can directly observe, all the stars, galaxies, gas clouds, and dust, they come up startlingly short. Roughly half of it, about 50%, is simply missing. This isn't a small accounting error. It's a gaping hole in our inventory of the cosmos, known famously as the missing Baryon problem. This presents a paradox that is both baffling and brilliant in its simplicity. We have a robust, time-tested theory telling us what the universe is made of, and our observations of the very early universe confirm it. Yet, when we look at the present-day universe, a huge portion of that material has seemingly vanished into thin air. It's as if we had a perfect manifest for a shipment of goods, confirming everything left the warehouse, but upon arrival, half the boxes are nowhere to be found. The immediate question is, where could it possibly be hiding? The answer, it turns out, is not in some distant, shadowy realm, but in the vast, almost empty spaces between galaxies and clusters of galaxies. This is the realm of the warm-hot intergalactic medium, or WIMP, a web of incredibly diffuse, superheated gas that fills the cosmic web. Detecting this material is one of the toughest challenges in observational astronomy. The gas in the WIMP is so hot, millions of degrees Kelvin, that it doesn't emit visible light. and it's so thin, with densities of perhaps just a few atoms per cubic meter, that it's virtually transparent. You can't just point a telescope at it and see it. Instead, astronomers have had to become cosmic detectives, using indirect and incredibly clever methods to find its fingerprints. Primary technique involves using the brightest beacons in the universe, quasars. These are distant galaxies with incredibly luminous cores, powered by supermassive black holes. As the light from a quasar travels billions of light years to reach us, it passes through these faint filaments of the WIMP. Specific elements within that hot gas, like oxygen and neon, absorb very particular wavelengths of that brilliant background light. By analyzing the quasar's spectrum, splitting its light into a rainbow of wavelengths, astronomers can see tiny, specific dips in the light where it has been absorbed. These absorption lines are the telltale sign that the light has passed through something, acting like a cosmic barcode that reveals the composition, temperature, and density of the invisible gas that caused it. Slowly, painstakingly, by combining data from many different quasars and using space-based observatories like NASA Chandra X-ray Observatory and ESA's XMM Newton that are sensitive to the high-energy light this hot gas emits, scientists have begun to find this missing matter. They are essentially mapping the invisible skeleton of the cosmos, the delicate filaments of gas that connect galaxies and clusters together in a vast cosmic web. The evidence is now strong that the missing baryons aren't truly missing. They've been here all along, hiding in plain sight in these immense, hot reservoirs. They were simply masquerading as nothingness, their faint signal lost in the darkness between the bright islands of galaxies. This anomaly is a powerful lesson in perspective and ingenuity. It shows that darkness isn't just the absence of light. It can be a veil that hides even the most fundamental components of reality. It forced astronomers to confront the limits of their tools and to develop new, innovative ways of seeing the universe. The solution to the missing baryon problem didn't require a rewrite of fundamental physics, but it did demand a radical shift in how we look for the ordinary in the extraordinary emptiness of space. It proves that sometimes the most profound mysteries aren't about what we don't know, but about what we haven't yet learned how to see. While we often think of the vast emptiness of space as a tranquil void, it is in fact a dynamic arena filled with an invisible hail of atomic bullets raining down on our planet from every direction. These are cosmic rays, not rays of light, but highly energetic particles, mostly protons and atomic nuclei, accelerated to nearly the speed of light by some of the most violent events in the universe. For decades, physicists have had a firm prediction about the maximum energy these particles could possibly have when they finally reach Earth, a theoretical limit based on one of the most successful theories in all of science. This boundary is known as the GZK cutoff, named for the physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin, who calculated it in the 1960s. Their work wasn't just an abstract exercise, it was a profound statement about the fundamental rules of the cosmos, a line in the sand that nature, according to our best models, should not be able to cross. Yet, when we built detectors powerful enough to measure the very highest energy particles, the data came back with a shocking revelation. Nature was not just crossing that line, it was sprinting right over it. The logic behind the GZK cutoff is both elegant and ironclad, rooted in Einstein's iconic equation E equals mc squared. It starts with the cosmic microwave background, that faint afterglow of the Big Bang that permeates all of space. This background radiation is made of low-energy photons, the particles of light. Now, imagine an ultra-high-energy proton, a cosmic ray that has been accelerated to within a fraction of light speed by a supermassive black hole or a colliding galaxy cluster. As this proton travels across millions of light-years of intergalactic space, it is constantly bumping into these ancient CMB photons. For most cosmic rays, these collisions are insignificant. But for a proton with energy above about 10 to the 20th electron volts, a specific, dramatic interaction becomes not just possible, but inevitable. The head-on collision is so violent that it provides enough energy to create entirely new particles, specifically a pion. This process saps a tremendous amount of energy from the original proton. The theory states that any proton lucky enough to be born with such incredible energy near the edge of our local supercluster of galaxies would have it relentlessly sapped away through these countless collisions long before it could ever hope to reach our detectors on Earth. The intergalactic space between us and the most distant cosmic accelerators should act as a kind of energy filter, ensuring that particles above this GZK limit simply never make it to our doorstep. This is where the paradox begins. Massive, sophisticated observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah are designed to catch these ultra-high-energy cosmic rays. They don't detect the particles directly, but instead observe the enormous cascades of secondary particles they create when they slam into the upper atmosphere, a phenomenon called an extensive air shower. The data from these painstaking experiments has been clear and consistent. They have recorded multiple cosmic rays with energies definitively above the GZK cutoff. These particles are arriving with energies that, according to our understanding of physics and the universe, they should have lost hundreds of millions of years ago on their journey here. It's as if a marathon runner showed up at the finish line not only without breaking a sweat, but with more energy than they had at the starting gun. The data is robust, the measurements are precise, and the conclusion is inescapable. Something is very wrong with our picture. This leaves scientists with a thrilling and deeply challenging set of possibilities to explain the paradox. The first possibility is that our understanding of particle physics itself is incomplete. The GZK calculation is based on the well-tested theory of special relativity and the standard model of particle physics. Could there be some new, unknown physics at these extreme energies that alters how protons interact with photons, allowing them to preserve their energy over vast distances? Perhaps Lorentz invariance, a cornerstone of relativity, is subtly violated at these energies, a radical idea that would fundamentally reshape our view of spacetime. The second possibility is that these cosmic rays are not coming from the distant universe at all. If their sources are much, much closer to us, within our own local group of galaxies, then they wouldn't have had enough time or traveled through enough of the CMB to experience the energy-draining collisions. This, however, creates its own puzzle. What local object possesses the unimaginable power to accelerate a single proton to such energies? We know of no celestial object within our local cosmic neighborhood, not even the supermassive black hole at the center of our own galaxy, that is capable of such a feat based on our current models of astrophysical accelerators. The GZK paradox is a perfect storm of a mystery, sitting at the crossroads of particle physics, astrophysics, and cosmology. It uses the universe itself as the ultimate particle accelerator, and the data it is giving us is contradicting a prediction we thought was rock solid. This anomaly forces a profound humility. It shows that even with a theory as successful as relativity, there may still be frontiers where it needs refinement, or that our catalog of cosmic engines is missing its most powerful members. These ultra-high-energy particles are the messengers from the darkest and most violent corners of the cosmos, and they are delivering a message we are still struggling to decode. They remind us that the universe is capable of generating energies and processes that still defy our imagination, and that the greatest breakthroughs often begin not with a confirmation, but with a contradiction that refuses to go away. Yet for all the grand, sweeping mysteries of deep space and dark matter, one of the most profound anomalies hits remarkably close to home, buried not in distant starlight but in the very rocks beneath our feet. It presents a puzzle that challenges our understanding of our own planet's past and the star that gives it life. Imagine the Earth over 4 billion years ago, a turbulent world of volcanic activity and vast oceans, yet already showing the first tantalizing chemical hints of life. According to everything we know about stellar physics, this scene should have been impossible. Our models of how stars evolved tell us that the young sun was significantly dimmer, about 30% less luminous than it is today. A star's brightness is tied to the fusion process in its core. As it ages and accumulates helium ash, its core contracts and heats up, gradually increasing its energy output. This means that billions of years ago, Earth should have been a global snowball, a frozen wasteland locked in a permanent ice age, with any liquid water buried deep beneath miles of ice. But the geological record tells a completely different and utterly contradictory story. The evidence for a warm, wet, and hospitable early Earth is written in stone quite literally. Ancient rocks found in places like Greenland and Australia, some dating back over 3.8 billion years, show mineral formations and isotopic signatures that could only have been created in the presence of vast quantities of liquid water. There are pillow basalts, formations created when lava erupts underwater, and sedimentary banded iron formations that precipitated out from ancient oceans. Perhaps most compelling are the zircon crystals, the oldest known fragments of the Earth's crust. These incredibly durable time capsules contain oxygen isotopes that clearly indicate they formed in an environment where liquid water was interacting with molten rock. The data is unequivocal. The early Earth was not a frozen prison. It was a world of liquid water oceans, a crucial prerequisite for the emergence of life that appeared shockingly early in the planetary timeline. This glaring contradiction between the astrophysical model of a faint young sun and the geological data of a warm young Earth is the core of the paradox, a mystery that forces us to rethink the delicate balance that makes a world habitable. So how did Earth solve this cosmic heating problem? How did it stay warm under a faint sun? Scientists have proposed a fascinating array of solutions, each painting a picture of a very different primordial world than the one we know today. The leading theory involves a planetary-scale greenhouse effect far more potent than anything we experience now. The early Earth's atmosphere was likely rich in powerful greenhouse gases like methane and ammonia, belched out in enormous quantities by widespread volcanic activity. Methane, in particular, is a highly effective heat-trapping gas, and a thick haze of it could have acted like an insulating blanket, keeping the planet cozy despite the weak sunlight. Another compelling idea points to the planet itself having a much darker surface. Without widespread continents and with more extensive, darker-colored oceanic crust exposed, the young Earth would have had a lower albedo, meaning it absorbed a greater percentage of the sun's faint light rather than reflecting it back into space like bright ice and snow would. Even a small difference in this planetary reflectivity could have made a dramatic difference in global temperatures, but the solutions don't stop there. Some researchers have proposed even more exotic mechanisms. Perhaps the early sun had a stronger solar wind, the stream of charged particles it emits, which could have interacted differently with Earth's magnetic field and atmosphere to generate more heat. Or maybe Earth's internal heat flow was significantly higher due to greater radioactive decay, providing a substantial source of warmth from the planet's own core that supplemented the feeble sunlight. The truth might be a complex combination of all these factors, a specific recipe of atmospheric composition, planetary appearance, and internal geology that worked in concert to keep the thermostat set just right. This paradox does more than just ask how Earth stayed warm. It forces us to confront the incredible dynamism and feedback loops that govern planetary climate. It shows that a planet's temperature is not just a simple function of its distance from its star, but a complex interplay of astronomy, geology, and chemistry. The faint young sun paradox ultimately transcends a single planetary story. It becomes a crucial data point in the search for life beyond our solar system. When we look at distant exoplanets orbiting other stars, we often classify them as lying within the habitable zone, the orbital region where temperatures could allow for liquid water. This paradox reminds us that this zone is not a fixed, static ring. It evolves as the star brightens over billions of years. A planet that seems perfectly positioned for life today might have been frozen solid in its youth, while a world that appears too close might have been temperate in the past. The Earth's own history suggests that a planet's atmosphere and geology can powerfully modulate the climate, potentially widening the real, effective habitable zone far beyond our simple calculations. This anomaly is a powerful lesson in humility, showing that the darkness we grapple with isn't always out in the cosmos. Sometimes it's a darkness in time, a gap in our understanding of our own origins. It proves that the most familiar objects, our sun and our planet, can hold some of the most disruptive secrets, challenging us to piece together the ancient story of how we came to be here at all. While we grapple with the climate history of our own planet, a different kind of anomaly takes us back to the very first moments of creation itself, challenging our understanding of the universe's original recipe. In the fiery crucible of the Big Bang, during the first 3 minutes of existence, the entire cosmos was a seething, dense soup of fundamental particles. As it expanded and cooled at an incredible rate, conditions became just right for the first atomic nuclei to form from a process known as Big Bang nucleosynthesis. This brief, explosive chapter forged the universe's initial supply of the lightest elements, hydrogen, helium, and trace amounts of lithium. For decades, the predictions from this model have been a crowning achievement of cosmology. The calculated abundances of hydrogen and helium deuterium match the observed values in the oldest regions of the universe with stunning, almost perfect precision. Yet there is one stubborn element that refuses to follow the script: lithium. The universe seems to have only about 1/3 of the lithium that our most trusted models insist should be there. This isn't a small rounding error, it's a factor of 3 discrepancy, a glaring outlier in an otherwise flawless prediction. This lithium problem forces scientists to confront a deeply unsettling possibility. If our model of the universe's first 3 minutes is so spectacularly accurate for every other element, why does it fail so dramatically for this one? The implications ripple through multiple fields of physics, pointing the investigative finger in several compelling directions. The first and most conservative possibility is that our understanding of the nuclear physics itself is incomplete. The predictions rely on precise measurements of nuclear reaction rates, or cross-sections, in the incredibly energetic conditions of the early universe. Perhaps there is an error in how we've measured how these primordial particles interacted and fused together. Maybe a key reaction rate is slightly off, or we're missing a crucial nuclear pathway that would have destroyed lithium-7 faster than it could form. Teams of physicists have spent years remeasuring these reactions in particle accelerators with ever greater precision, yet the problem persists, suggesting the answer may lie elsewhere. This leads to a second, more dramatic possibility. that unknown astrophysical processes in the ancient universe systematically destroyed this primordial lithium after it was created. The oldest stars in our galaxy, which formed from the pristine gas of the early cosmos, act as cosmic time capsules, preserving the chemical signature of Big Bang nucleosynthesis. And it is in the atmospheres of these ancient stars that we see the lithium deficit most clearly. Could some process within these first stars have burned away the lithium? Perhaps the convective zones of these low-mass, metal-poor stars allowed lithium to be dragged down into hotter interior regions where it was easily fused into heavier elements. While models of stellar physics can account for some depletion, they struggle to explain the full factor of 3 shortfall across all these ancient stars, leaving a significant gap in the explanation. The most thrilling and radical hypothesis is that the lithium problem is a direct hint of new physics operating in the infant universe. The predictions of Big Bang nucleosynthesis are built upon the standard model of particle physics and our well-tested theories like general relativity. What if something beyond that standard model was at play in those first few minutes? Some theorists have proposed that the presence of exotic particles, like certain types of dark matter, could have altered the nuclear reaction network. These particles might have affected the density of free neutrons at a critical moment or provided a new channel for energy exchange, subtly shifting the balance of elements produced. Others have even suggested that the fundamental constants of nature, like the fine structure constant, might have been slightly different in that ultra-dense, high-energy environment, tweaking the nuclear recipes just enough to leave us with less lithium than we expect. The profound significance of the lithium problem lies in its humility. It is a reminder that our most foundational stories, the ones we hold up as pillars of modern science, can still contain deep and unresolved mysteries. It shows that darkness isn't just the empty space between galaxies. It can be a gap in our knowledge of the universe's very first moments. This tiny discrepancy in the amount of a single element serves as a permanent caution against intellectual arrogance, proving that even our greatest triumphs in understanding the cosmos come with a footnote that reads, "More to be discovered." It is an anomaly that connects the largest scales of cosmology to the smallest scales of particle physics, a tiny thread that, when pulled, could potentially unravel and reweave our entire understanding of cosmic dawn. But the mysteries at the heart of our galaxy don't stop with the high-energy glow of gamma rays. If we tune our instruments to a slightly different frequency, another enigmatic signal emerges from the darkness, one that is both intimately related and distinctly different. This is the galactic center GVXS, a puzzling surplus of lower-energy photons detected by the same Fermi gamma-ray space telescope. While the gamma-ray excess is like a brilliant, high-pitched scream of energy, the GVXS is more of a persistent, lower-frequency hum, a steady and unexplained background radiance emanating from the same chaotic region around the supermassive black hole Sagittarius A star. The GV stands for giga-electronvolt, a specific measure of energy that places these photons in a middle ground, less energetic than the gamma rays but still far more powerful than the light our eyes can see. This specific energy range makes the mystery all the more compelling and difficult to pin down, sitting in a sweet spot that has theorists fiercely debating 2 very different cosmic explanations. On one side of this scientific debate are the proponents of a dark matter origin. This theory is incredibly alluring because it offers a potential solution to 2 great mysteries at once. The leading candidate for dark matter remains the WIMP, the weakly interacting massive particle. Theoretically, when 2 WIMP collide, they should annihilate each other, converting their mass directly into energy and producing a shower of secondary particles, including pairs of electrons and positrons. These particles would then radiate away their energy as they spiral through the Milky Way's magnetic fields, a process known as inverse Compton scattering that generates photons precisely in the GeV energy range that we observe. The galactic center is predicted to be the densest region of dark matter in the entire galaxy, the very place where such annihilations should be most frequent and produce the brightest signal. For many, the GeV excess is the most promising indirect evidence we have that we are finally on the verge of detecting the universe's most elusive substance, not in a lab, but by observing its final death throes in the void of space. The other major explanation is far less exotic but no less fascinating, pointing to a vast population of stellar objects we have yet to fully catalogue. The Milky Way's core is an incredibly crowded and tumultuous place, packed with millions of stars, including rapidly spinning neutron stars known as millisecond pulsars. These are the ancient, reanimated corpses of massive stars, spun up to incredible speeds by accreting material from a companion star. As they rotate, they beam out powerful lighthouse-like pulses of radiation across many wavelengths, including GeV energy photons. A large population of these faint, distant pulsars, each too dim for our current telescopes to resolve individually, could collectively produce a smooth, diffuse glow that perfectly mimics the observed excess. This astrophysical explanation is often seen as the more conservative option, suggesting the answer lies not in new physics, but in a more nuanced understanding of the stellar demographics in our galaxy's bustling downtown. The intense effort to distinguish between these two ideas has driven astronomers to ever more creative methods of analysis. The key lies in the texture of the signal itself. A dark matter annihilation signal would be inherently smooth, spread evenly across the region of highest dark matter density. A population of point sources like pulsars, however, would create a signal that is slightly clumpy or granular, with statistical fluctuations that might be teased out with enough data. Researchers have spent years applying sophisticated statistical models to the Fermi data, searching for any hint of this telltale lumpiness. Some studies have claimed to find evidence of such point sources, bolstering the pulsar argument. Others have countered that the signal remains stubbornly smooth, keeping the dark matter hope alive. This back and forth exemplifies the cutting edge of modern astrophysics, where the answer isn't found with a bigger telescope alone, but through deeper and more sophisticated statistical mining of the data we already have. This ongoing puzzle underscores a profound truth about our exploration of the cosmos. The center of our own galaxy, a mere 25,000 light-years away, remains as enigmatic and challenging to understand as the most distant quasar. It is a region shrouded not only in literal darkness by thick clouds of interstellar dust that block our view in visible light, but also in a metaphorical darkness of incomplete knowledge. The GeV excess is a ghost in the machine, a persistent signal that refuses to be easily categorized. It reminds us that the universe's greatest secrets are often hidden in plain sight, encoded in the light that washes over us constantly. Whether the final answer points to the discovery of dark matter or to a new census of hidden stellar corpses, this anomaly guarantees that the heart of the Milky Way will remain a focal point of scientific curiosity, a place where data and darkness continue their captivating dance. Yet for all the grand cosmic puzzles we've explored, one of the most telling anomalies hits remarkably close to home, quite literally shaping our understanding of our own galactic neighborhood. Picture our Milky Way not as an isolated island universe, but as the gravitational center of a vast, swirling entourage, a flock of smaller satellite galaxies caught in its immense pull, each one a dwarf system with its own story to tell. According to our most sophisticated supercomputer simulations of how galaxies form within the cosmic web of dark matter, this entourage should be enormous. These virtual universes, running the equations of gravity and physics over billions of years of evolution, predict that a galaxy the size of the Milky Way should be surrounded by not dozens, but hundreds of these smaller satellite galaxies. They are the predicted remnants of the earliest building blocks of the cosmos, the leftover pieces from the hierarchical construction of our galactic home. Yet, when astronomers began to actually count them, the observational data told a very different story. For a long time, we could only find a paltry handful, 11, then maybe 20. This glaring mismatch between theoretical prediction and observational reality became one of cosmology's most persistent headaches, famously dubbed the missing satellites problem. This wasn't just a case of being bad at counting. The discrepancy pointed to a potentially serious flaw in our understanding of the universe's fundamental architecture, an architecture built upon the invisible scaffolding of dark matter. The simulations that predicted this abundance of satellites are based on the highly successful lambda-cold dark matter model, which describes a universe dominated by dark energy and filled with slow-moving dark matter particles. In this model, dark matter halos form first, and their gravitational pull draws in the ordinary baryonic matter that eventually forms stars and galaxies. The simulations showed that thousands of small, dark matter clumps or subhalos should survive the violent process of galaxy formation and continue to orbit a larger galaxy like our own. The logical assumption was that a significant fraction of these dark subhalos would have accreted enough gas to ignite star formation, lighting them up as the visible dwarf galaxies we should be able to see. The fact that we saw so few suggested one of two deeply unsettling possibilities. Either our theories about dark matter were wrong, or our understanding of how stars form in these tiny, fragile systems was severely incomplete. The plot began to thicken with the arrival of a new era of astronomical surveys, most notably the European Space Agency's Gaia mission. Gaia's unprecedented precision in mapping the positions and motions of billions of stars in our galaxy has been nothing short of revolutionary, and it turned its powerful eye toward this very problem. By tracking the subtle movements of stars in the Milky Way's outer halo, Gaia began to uncover new, incredibly faint satellite galaxies that had previously been lost in the darkness, hidden behind the foreground clutter of brighter stars. These newly discovered systems are the ghosts of the galaxy ultra-faint dwarfs so dim that they contain only a few hundred stars, yet are spread across a volume of space larger than some full-fledged galaxies. Thanks to these efforts, the official tally of known satellite galaxies has grown, but it still falls dramatically short of the hundreds predicted. We've found more of the missing pieces, but the puzzle is still far from complete. This ongoing search has forced a fascinating refinement of our models, leading scientists to propose a compelling solution that doesn't require throwing out our entire understanding of dark matter. The answer may lie not in the darkness itself, but in the ordinary matter that tries to shine within it. The process of star formation, especially in these tiny, vulnerable systems, is far more complex and inefficient than we once thought. When the first generations of stars began to form in these small subhalos, their effects were catastrophic. The first massive stars would have lived fast and died young, exploding as supernova. These explosions would have unleashed powerful winds, easily strong enough to blow all the remaining gas, the raw fuel for future star formation, clear out of the weak gravitational grip of the dwarf galaxy. Without gas, no new stars could form, and the galaxy would effectively die, leaving behind only a dark, starless halo of matter. Furthermore, the intense ultraviolet radiation from those first stars could have heated up the surrounding gas throughout the entire early universe, making it even harder for later generations of small halos to cool down and condense into stars. This concept, known as reionization, could have sterilized countless small dark matter clumps, preventing them from ever lighting up in the first place. So, the missing satellites problem may not be a problem of missing dark matter, but one of missing light. The hundreds of dark matter subhalos predicted by the simulations are likely still there, orbiting our galaxy right now. They are just almost entirely dark, composed of their original dark matter with perhaps only a handful of ancient stars, if any at all. This elegant solution beautifully marries the robust predictions of dark matter theory with the stubborn observational data, but it also presents a new and incredible challenge. How do you map the invisible? The hunt is now on for these dark satellites, not by looking for their light, but by searching for the subtle gravitational footprints they leave behind. As these massive but invisible objects move through the outer reaches of our galaxy's gas halo or drift in front of distant background stars, they should create tiny, detectable distortions, a ripple in the fabric of spacetime or a brief flicker of a star's light. Finding this evidence would be a monumental confirmation of our entire cosmological model. This anomaly perfectly embodies the dance between data and darkness, showing that what we don't see can be just as important as what we do. It reminds us that our galaxy's true structure is written not just in the stars we can easily observe, but in the vast, unseen majority of dark matter that holds it all together, a hidden framework whose full shape we are only beginning to trace. And just as we grapple with the invisible architecture of our own galactic neighborhood, we turn our gaze to the deepest reaches of time and space, where our most powerful telescopes have revealed an anomaly that strikes at the very heart of our cosmic origin story. The quest to understand the infancy of galaxies began with a tremendous gamble. In 1995, astronomers pointed the Hubble Space Telescope at a seemingly empty patch of sky near the Big Dipper, a region no larger than a grain of sand held at arm's length. For 10 consecutive days, Hubble's sensitive instruments collected every single photon of light that arrived from this void, a painstaking exposure that many thought would reveal nothing but empty blackness. The resulting image, known as the Hubble Deep Field, did the exact opposite. It revealed a universe teeming with galaxies, over 3,000 of them, each a faint smudge of light that had traveled for billions of years to reach us. This revolutionary image was more than a pretty picture. It was a time machine allowing us to look back and directly observe the universe in its youth. But with this new view came a profound and unexpected shock, one that would only deepen with subsequent deep field observations. The ancient galaxies in these portraits didn't look like the disorganized, infant blobs we expected. Instead, many of them appeared surprisingly mature, well-structured, and far too advanced for their tender cosmic age, forcing a dramatic rewrite of our theories on how the universe built its first cities of stars. Our standard model of galaxy formation is a story of gradual, hierarchical growth, a slow cosmic dance set to the rhythm of gravity. The theory goes that after the Big Bang, the universe was a nearly smooth soup of dark matter and gas. Tiny fluctuations in this primordial density grew over hundreds of millions of years as dark matter clumped together to form halos. These halos acted as gravitational seeds, pulling in ordinary gas that eventually cooled, condensed, and fragmented to form the first stars. These first stars then grouped into protogalaxies, which over billions of years merged and cannibalized each other to form the large, majestic spirals and ellipticals we see in the modern universe. This process is supposed to be slow and messy. The earliest galaxies, we believed, should be small, irregular, and chaotic blobby, turbulent collections of young stars, lacking the defined spiral arms, central bulges, and orderly rotation of their modern counterparts. They should be cosmic toddlers, all energy and no structure. The deep field data completely upends this expectation. When astronomers analyzed these deepest of images, they found galaxies that existed when the universe was a mere 500 million to 1 billion years old, a fraction of its current 13.8 billion year age. Yet, a significant number of these galaxies already displayed clear, recognizable structures. Some showed evidence of rotating disks. Others had distinct central bulges, the dense conglomerations of stars that form the hearts of modern galaxies. There were even examples of grand design spiral arms and massive, red, dead galaxies that had already exhausted their star-forming gas. This is the core of the anomaly. It's as if we discovered a photograph of our grandparents as young children, but in the photo, they already have the fully developed features, posture, and demeanor of adults. The data suggests that the universe's first galaxies assembled themselves with a speed and efficiency that our current models simply cannot explain. They grew up too fast. This discovery forces a fascinating and humbling reevaluation of the early universe's physical conditions. What could have driven such rapid and precocious growth? One compelling line of thought focuses on the role of the very first stars, known as population Roman III stars. These hypothetical giants, hundreds of times more massive than our Sun, would have lived ferociously brief lives before exploding in cataclysmic hypernova. Their violent deaths would have seeded their surroundings with the first heavy elements and unleashed powerful shockwaves that could have triggered incredibly efficient and rapid bouts of star formation in neighboring gas clouds, essentially kickstarting galaxy assembly on a fast-forward mode. Another possibility is that the early universe was a much denser and more dynamic place, with gas falling into dark matter halos at a far more furious rate than it does today, providing a rich and abundant fuel supply for frantic star birth. There's also the intriguing, though highly speculative, idea that the nature of dark matter itself might be different than we think. Perhaps the dark matter particles in the early universe were warm or interacted with each other in ways that allowed small structures to form more quickly, providing a ready-made framework for galaxies to build upon at a startling pace. The Hubble Deep Field Anomalies and their even more revealing successors from the James Webb Space Telescope serve as the ultimate reminder that the darkness of the cosmos is not an empty void, but a vast historical archive. Every time we build a telescope with greater power to gather light, we are effectively building a better time machine, allowing us to read earlier and earlier chapters in the universe's biography. And with each new chapter we read, we are finding that the story is more surprising, more dramatic, and more inventive than our theories had ever predicted. These distant, mature galaxies are not just scientific curiosities. They are profound messengers from the dawn of time, telling us that our universe is capable of engineering and complexity on a scale and at a speed that we are only beginning to comprehend. They represent the ultimate disruption at the intersection of data and darkness, proving that when we push our instruments to their absolute limits, the cosmos rewards us not with final answers, but with better, more beautiful questions. From the fleeting whisper of the wow signal to the mature galaxies staring back at us from the edge of time itself, these 20 disruptive anomalies form a powerful testament to a single, profound truth. Our understanding of the cosmos is not a finished map, but a living, breathing draft, constantly being revised and redrawn. Each one of these mysteries, from the coordinated river of dark flow to the paradoxical faint young sun, serves as a stark reminder that the universe is far stranger, more dynamic, and more inventive than our most ambitious theories could ever predict. They are not failures of our science, but rather its greatest successes prove that our methods of questioning the darkness are powerful enough to reveal just how much we have yet to learn. This journey through the intersection of data and darkness reveals a fascinating pattern. Time and again, the process of discovery begins not with a eureka, a moment, but with a subtle inconsistency, a data point that refuses to fit neatly into the established model. It starts with a spacecraft slightly off course, a star dimming in an impossible way, or a signal from the void that arrives and vanishes before we can even turn our heads. These anomalies are the universe's way of whispering a hint, offering a clue wrapped in a puzzle. They force us out of our intellectual comfort zones, compelling scientists to question long-held assumptions, to build better instruments, and to imagine possibilities that once belonged solely to the realm of science fiction. The pursuit of these mysteries, perhaps even more than their eventual solutions, is what truly drives human knowledge forward, pushing the boundaries of physics, engineering, and our own imagination. What makes this ongoing quest so exhilarating is that it is fundamentally a human story. It's a story of curiosity, perseverance, and collaboration that spans the globe. It's about radio astronomers sifting through reams of data, citizen scientists spotting a strange star from their home computers, and teams of researchers spending years chasing down a thermal radiation explanation for a phantom acceleration. Every anomaly on this list represents countless hours of work, dead ends, debated theories, and the shared excitement of staring into the unknown together. This collective endeavor reminds us that we are all part of this grand exploration, each of us contributing to the piecing together of the cosmic puzzle, whether by following the latest data from the James Webb Space Telescope or simply by looking up at the night sky with a sense of wonder. So as we conclude this journey, the greatest takeaway is not a list of answers, but an invitation to maintain a sense of radical curiosity. The next great discovery might be hiding in data that has already been collected, waiting for a fresh perspective to see the pattern. It might be arriving on a particle from a distant galaxy we cannot yet name, or encoded in the light of a star that no one is currently watching. The universe is under no obligation to conform to our expectations, and that is what makes its study the most exciting adventure there is. We are living in a golden age of astronomy, where our tools are more powerful than ever, and our maps of the cosmos are revealing new mysteries faster than we can solve the old ones. The intersection of data and darkness is not a barren crossroads. It is the most fertile ground for discovery we have ever known. Now we want to hear from you. Which of these 20 anomalies captured your imagination the most? Was it the tantalizing possibility of the wow signal, the cosmic rearranging required by the Hubble tension, or the ghostly presence of ultra-diffuse galaxies? Let us know your thoughts in the comments below. Share your theories and which mystery you think holds the key to the next great breakthrough. If you enjoyed this journey to the edge of our understanding, be sure to like this video and subscribe to the channel for more deep dives into the wonders of space and science. Thank you for watching, and never stop looking up. If this journey through the cosmos has sparked your curiosity, you can help keep that sense of wonder alive for everyone. Liking this video and sharing it with others directly supports this channel, allowing us to dive even deeper into the universe's greatest mysteries for our next adventures together. Make sure you never miss an exploration by subscribing to the channel and tapping that notification bell. It's the best way to journey with us as we continue to explore the farthest reaches of space and thought. Now, we'd love to hear which of these 20 anomalies resonated most with you. Was it the haunting brevity of the wow signal, the structural defiance of the KBC Void, or the mature galaxies that seem to grow up too fast? Share your pick in the comments below and tell us why you think it holds the greatest potential for a world-changing breakthrough. Your perspective is unique, and your insight might just be the one that helps illuminate the darkness